Hi, welcome to the fun probability problem solving sections. And today we're going to solve a very, very classical probability problem. Yes, if you have a random variable x, it has a binomial distributions, then the x is going to converge to a Poisson when the n approach to infinity. And this is a very, very good properties we can use when we try to find the probability for the binomial distributions layer. So we can estimate and predict by using the Poissons because when the n is large. Okay, so basically if you take a look here, that means when the x equal to I, and then so that when the n approach to infinity, then the probability x equal to I will approximate to the probability mass functions, for the Poisson. So PMF is here. All right, so let's take a look. Let's go to the the whiteboard and start to solve these problems here. Okay, so let's go to the whiteboards here. All right, so here is the whiteboard here. Okay, so in order to solve these problems here, one of the equation we're going to use is from our calculus class. So this is the one thing here we need to know. So this is like the limit n approach to infinities. Here, this is 1 plus 1 over n to the nth power, and this is the definition of this e numbers, right? So in here, be careful here, the e, this is e to the first power, basically, right? So these things when we learned in the calculus. So if here this is what is this is here. So if you have a 2's here, this will be approximately to the e to the 2. All right, so the second power is here. So that is the one thing we need to be careful. Okay, after we know that, then the remaining, the proof part will be pretty simple here. Will just be the algebras here. Okay, let's start out with x equal to I is the binomial distribution. So we know this is ni, then the p, the I, and the 1 minus p, the n minus I, right? Okay, so just like we use our combination, so this is n factorial, I factorial, n minus I factorial, then this is pi, and this is 1 minus p to the n minus I, because we know when they approach to the Poissons here, we also know is approach to the lambda is equal to np's, right? Lambda equal to np, so I can change the p is equal to what? Lambda over n here. All right, so now I'm just replace this one here. So this is n factorial, and this is I factorial. So this the factorial is missing here, and this is n minus I factorial. Okay, so the p, I'm going to do the ni, right, to the I n lambda. Okay, so the n lambda, I don't know what I'm thinking. So this is n lambda to the i's power, and then this is 1 minus lambda over n to the n minus I powers here. All right. Okay, so now in here, then we say here this is the ni, and then this is I factorial, and this is n minus I factorial, and then this one's here I can put this is I to the nth power, then I have here is n to the i's power, right? So this is how I separate these terms. I can kind of do like this. The reason why I want to do that because when the n approach to infinity layer, I want to separate the number without the n's here. All right. Okay, so now for the other terms here, this is just 1 minus lambda to the n then this is n's power, and then this is 1 minus lambda over n to the negative i's powers here. All right. Okay, so now let's take a look here. Now I'm going to put a limit. So here is limit n approach to infinity p the x equal to I here, right? So first I can move all the things that has nothing to do with n to leave it out. So I can have I to the nth power. Then I have this is I factorial, correct? Okay, so then I will have a limit n approach to infinity. So I have this is ni factorial, then this is n minus I factorial, right? Then I have this is ni, then ni factorial, then I have this is ni, correct? Okay, so then here I have this is 1 minus lambda n, and to the n, and this is 1 minus lambda n. If you like, you can just switch that one here. So this will be over 1 minus lambda n to the i's powers, right? Okay, so now let's take a look here. So for this ones here, so when n approach to infinity, this number going to approach to what? Approach to zeros, right? So the whole distance, so then it's going to approach to 1 to the i's power. So what is the whole distance approach to? The whole distance approach to 1, right? It's because the limit n approach to infinity, the lambda over n is going to approach to 0, because lambda is a fixed constant, right? So the lambda over n is going to approach to 0. So now the 1 minus 0 is 1. So this term will approach to 1 here. Okay, now let's take a look at these terms here. This term, the limit when the n approach to infinity, this is the one I mentioned. So here we need to use this calculus equation. So what is this one going to approach to? This going to approach to e. Look here, the top here is negative lambdas, right? So that's what I highlight here is 1. So this is e to the first power. So what I need to here, so it's e to the what? This is e to the lambda, right? So this is e to the lambda. All right, so now the only things right now I have is these terms here, right? So I have these terms here. This is the, okay, so this is the I lambda. So this is I just I think I just erased something. So this is I. So this is lambda to the. So what is lambda to the? So this is n. Oh, I to the nth power. Right. So the I to the nth power. Hold on. So this is lambda to the I. Oh, lambda to the nth power. Oh. So lambda, okay, so here I need to be careful here. So this is, oh, come on here, right? So this will be the lambda to the i's power. All right, so that's what I made a mistake here. So lambda to the i's power, the n to the i's power. Okay, so here when we take the things out, I need to be careful. So this one's here, this is lambda to the i's powers here. All right, so now it's set. So now I need to work on this, correct? So this one's here. All right, so let's take a look at the n factorials here. So n factorial, so this is n minus I factorial, and this is to the ni. So the n factorial, so n factorial, I can change it to the n minus 1, and n minus 2, and all the way to n minus I plus 1. So then the n minus I factorials, right? Then here this is n minus I factorial. Then this is to the ni. All right. So now in here, you take a look here. So this ni and this can cancel. So these things here we just left is, will be n times n minus 1, n minus 2, and da to the n minus I plus 1 here. All right, so this is to the ni. All right, so here the ni powers here, that means this will be the n minus 1, n minus 2, to the n minus I plus 1. So you have n, n's here, right? So this is i's powers here. Now you take a look. Now in here, I know this one, when n approach to infinity, what this one will approach to once, right? So for this term, the n minus 1 over n. So what is this one approach to? It will approach to 1 also, because is n over n, we use the highest dominant term. So this one are going to approach to what? Approach to 1. So I know the whole distance. What is this thing going to approach to here? This is going to approach to what? Approach to once here. That is how we say, okay, so now I have I factorial lambda I, and then in these three terms, I only have what? E to the, the negative lambda. All right, so this is what? This is the Poisson. So this is what is it? This is a PMF for the Poissons, right? With lambdas here. So we proved it, right? So we proved when the n approach to infinity, then this will be approach to the x going to converge to the Poisson distribution with lambda, and the lambda is we defined as n times p. Okay, that's it. And so it's a pretty very, very classical proof here. And okay, so that's it. Now let's see here. All right, so let's turn the recording off here. Oh, here, okay, so, all right, so now that's it. Okay, have a good day. Bye-bye.